All right, so before I forget, I want to thank the organizers for inviting me, and it's been a very wonderful conference so far. I'm going to talk a little bit about some new work that I've been doing with my collaborators, Rafael González D'León and Chris Hanusa. All right, so this is the plan. We'll see how it works. I've never given a 90-minute lecture before, and I have no sense of how fast this is going to go. But this is the plan. So today, I'm going to start by doing an introduction on flow polytopes. William did a really fantastic job motivating and giving the history of some of this stuff earlier this week. But I'll also still go through some of the basics, if only just to set the notation that I prefer. We'll talk about faces, volume, frame triangulations, and the dual lattice structure, and so on. So today we're going to stick with a very simple case where the net flow of the flow polytope is just strength 1. So I'm looking today at graphs with one source and one sink and just one unit of flow going into the source. Tomorrow I will be generalizing some of the story, really diving into some more of the details of the combinatorics and generalize a lot of the story to this more general net flow of the flow polytope where you can have many sources and then one final sink. Okay. All right, so, and I also want to make sure I do my job. So the first 3 slides, permutahedra, I'll focus on this side. Associahedra, again, focus on this side for now. The other side will make sense later on. A little bit beyond. And then way beyond. All right, so I just wanted to lead with these pictures. There are beautiful lattice structures that come from this story. And yeah, lots of beautiful combinatorics and pictures. Okay, so again, just begin at the beginning. Flow polytopes. I have an acyclic directed graph G, right? And my vertices, I'm gonna label them from 0 to n. I assume there are m edges, they can be repeated, there can be multiple edges. Here's my net flow vector. All right, so I'm assuming that these are non-negative integers, and then the final coordinate is just negative, the sum of the first n coordinates. And for example, here's a graph. All right, so I always assume that my graphs, my edges are directed from the left to the right. And here, right, I'm picturing I have unit flow going into here, so one unit of flow going into there, and then it flows through the pipes. The pipes don't leak, so flow is conserved at every single vertex. Right, we can check on, for example, this vertex. All right, I have, let's see, 0.4 units and 0.3 units coming into here. I also have to have a total of 0.7 units of flow leaving, right? But at the end, all the flow gathers and it leaves the sink. All right, so this is the 1, 0, 0, 0 minus 1 flow. All right, alternatively, so the flow polytope is just the set, the convex hull of all possible flows on this graph, but you can also think of this as given by this matrix equation, where n sub g is the signed incidence matrix of the graph G. And one of the facts of flow polytopes is that it has dimension m minus n, where m is edges, number of edges, and I'm indexing of vertices like this, so it has n plus 1 vertices, but the dimension is m minus n.
May I ask a question? What are these blue numbers?
Oh, just an arbitrary flow.
I thought it's 1. You said it's 1 coming in.
Did I make a mistake?
What are the blue numbers?
The blue numbers here on the edges,
Yes.
that's flow. Okay, so one more time.
But if 1 is coming in, how come 3 go out?
Oh, yes. Sorry. Those,
Okay, thank you.
make it just a little bit bigger, like that, yep. Yep. I also may have made a mistake, so maybe it didn't add up, but I think it does add up. All right, 1 unit leaves at the end. Okay. Okay, William also mentioned faces of flow polytopes, so I just wanted to mention this result by Hilla. Right, faces of a flow polytope are supported on certain subgraphs of G, right? And this subgraph H of G has to be able to contain an A flow. Right, he showed that vertices are supported by subgraphs, which are trees, right? And as a corollary, we can determine the vertices of such a flow polytope. The vertices of such a flow polytope are indexed by routes, which are just maximal paths from the source to the sink. And again, you've seen this picture before if you went to William's talk. All right, let's look at the simple example where this is my graph. Right, and I'm picturing 1 unit of flow going in, 1 unit of flow going out. Right, and so in general, flow polytopes are high dimensional, right? Its ambient space is the number of edges of the graph, but its actual dimension is lower, right? M minus n. So we can, a lot of the times, just project. And here I'm using the same projection that William did. For example, I know that if 1 unit of flow goes into there, right, this lower edge has to have flow summing up with that top edge. It has to sum to 1, so I know that lower edge has to have flow 1 minus x. All right, so for example, I'm just going to, whatever flow I get in here, I'm just going to project to 2 coordinates, x and y. All right, and for example, right here, if I put all the flow down here, that means my coordinates are 0, 0. Did I flip this? I flipped this. Do a reflection. This is supposed to be the other way. But I don't want to erase this right now, so I'm just gonna leave it. All right, so one more time. The vertices correspond to maximal paths, which I'll call routes, from the source to the sink. Okay, so Danilov, Karzanov, and Koshevoy came up with a combinatorial method to produce many triangulations of the flow polytope, which depends on something called a framing. So for each vertex V, a framing is just an ordering of the incoming edges into V, and then separately an ordering on the outgoing edges of the V. And once I have a framing at every single vertex, right, then I say a framing of G is the set of all framings at every vertex collected together. So I'm going to take a convention that's slightly different. So for those who are used to DKK framings, right, I'm going to take the convention that I also include the framing at the source and the sink. Right, it's just a little technicality, but it makes everything a little bit better defined for us. Right, so for example, right, I drew this graph before, right, but a sane person probably would have drawn it maybe like this. Right, it's a good way to organize it, but the way I'm drawing it in this talk actually matters. So I'm going to pictorially define the framing. So for example, if I draw such a picture, then I mean the framing. For example, look at vertex 2. Right, so there are 2 edges incoming to vertex 2. I'm going to order that 1 and then 2. So that's the framing order on the incoming edges. And then there are 2 edges leaving as well. Visually, I define the framing from the bottom to the top. So all the incoming edges, outgoing edges are ordered. And so that defines a different framing compared to that other drawing. The graph is the same, right? But here, let's look at vertex 2 again. The incoming edges are ordered the same way as before, but because of the way, well, maybe that's not the greatest. Let's look at, actually this graph I just noticed has a lot of symmetries. I've actually never drawn it like this ever. I did it for this talk. But anyhow, when I frame it like this, right, this is the lower, this is the upper. Right, so these 2 framings are different. Now I'm doubting myself. Yes. At 4, the incoming order is different because now the short edge is in between. Right, anyhow, there are many, many different framings for each directed graph. Right, so a framing at a vertex V induces total orderings on the set of prefixes coming into V and on the set of suffixes leaving V. And so, for example, when I say suffixes of V, I just mean look at a vertex V and look at all the paths from V to the end. Okay, quick exercise. Look at this pair of paths on the graph on the bottom. And so this is a suffix of V, P is going on top like this, Q is going down like this. Right, is P greater than Q or P less than Q? There's one detail I haven't told you yet. All right, so how does the framing at a vertex of the edges induce a framing on suffixes? Well, the way we do it is you take these paths and when it leaves V, you follow it on the largest common component. Right, so P and Q are the same up till here, and then they start splitting. Right, so the order on P and Q depends on the outgoing order here. And so is P less than Q or P bigger than Q here? I remember my framings, I always frame the edges smaller. Yeah. So here, right, if I draw the framing, this is framed 1, this is framed 2, so P is greater than Q.
Sort of a lexicographic.
Yeah. Right, so you just leave V and you follow it along the largest common subroute, and then you look at the order where it first splits. Right, and then there's an analogous ordering. If you just flip the whole rule, there's an analogous ordering on the prefixes. If you looked at prefixes, you have vertex V, right? You follow the prefixes as far back on a common subroute as possible, and then where they last split, I guess, or where they merge, the incoming order at that vertex determines the ordering of the prefixes. Okay. All right, so there's a lot of background in this build-up to constructing a frame triangulation. Okay, so two routes V and Q are in conflict at a vertex V if when I look at the prefixes PV and QV, they have the opposite ordering from the suffixes leaving V. And then I say P and Q are coherent if they are not in conflict at any vertex. Okay. So I built in some of the exercise session into here, just kind of basic things about frame triangulations. And that's this first example, I'll make it a little bit bigger. Are P and Q coherent? And Philippe said yes very quickly. How did he know so quickly? They have no vertices in common, right? So you don't have to really check anything. They are never in conflict because they just don't intersect anywhere.
Don't you check beginning and ending?
You can check beginning and end, but the beginning has no incoming. No prefixes. And same with the end, right? There are no suffixes, so it's empty conditions. So yes, no intersections. Okay, next pair, part B. And so P and Q, they share this common edge, but then, right, it splits here and it splits here. So according to the definition, you look at the relative ordering here compared to the relative ordering there. Right, and let me just put in those framing numbers, the framing order. Right, this comes first, this comes second, this comes first, this comes second. All right, so now the relative orders coming in and going out are different. So this is not coherent. Right now you can say they have a conflict at vertex 3, for example. All right, one more. Are they coherent? Yes, but it takes a while to check, right? You have to look at every single vertex, right? Look at the prefix, suffix, compare, right? Sometimes if your graph gets really crazy and it has edges that twist, it's visually sometimes a little bit difficult to check, but yes, this one is as well.
Can I ask a question?
Uh-huh. B.
So when the two paths follow the same, two routes follow the same edges, they're still bordered.
They're,
The middle one, like the purple one,
yeah, the purple one.
it still has a one and a two, or they.
It's this. They're both on the same. So they coincide, right? They intersect. So you should think of them as being ordered the same along that common edge or common subpath. You can only compare their orders when they're different. So that's why. So maybe my example, if it was more complicated, this could have been a common subpath. I could have added vertices in there, right? And if this is my new example, right, I can't compare their orders until P and Q, for example, split here. And then I say, even if this is my vertex V, right, then I say the outgoing order from V is determined the first time they split. And then the incoming order into V is determined, right, the first time, the last time they merge. Okay. Okay, almost there to the big theorem. Okay, so we have a notion of when routes are coherent. A clique is a set of pairwise coherent routes. This set is partially ordered by containment, right? And given a clique, we define its rank or its dimension to just be one less than the size of the clique. And I'm going to let delta C denote the convex hull of the indicator vectors of routes. Right, so now C, a clique, right, I have a bunch of routes. They're all coherent. And so for each of them, right, I just look at you can call it the characteristic vector sometimes, or the indicator vector. Right, so a route is now a point, right, in R to the E space. Take the convex hull of that defines a simplex. Or, well, it will define a simplex. All right, so the result of Danilov, Karzanov, and Koshevoy is if we start with a acyclic directed graph with a framing, then if you look at all the maximal cliques, so you look at routes, you determine when they're coherent, and you make these coherent collections as big as possible, you look at the convex hull, that is going to be a top-dimensional simplex in a triangulation of the flow polytope, and this triangulation is regular and unimodular. And moreover, they tell us exactly when two simplices share a facet. Two of these simplices defined by maximal cliques, they share a facet if and only if they differ in exactly one route. So kind of like a flip, like a basis exchange thing.
Sorry.
Mm-hmm.
Is it obvious that every maximal clique has the same number of drops?
No, but it comes out in the proof. Yeah. Okay. Back to really the simplest example I can draw. And even then, I already made a mistake, so we'll see. Just remember now, this is my x-axis, and this is my y-axis. Oh boy, okay. So, simple example, this is my graph with that framing. All right, this is a square. We know that in order to give a unimodular triangulation of it, it will have two pieces, so there are two maximal cliques. All right, I will draw them for you. So first of all, because this graph has a planar embedding, all right, this framing has a planar representation, then visually it's easy to see when routes are coherent. Routes are coherent as long as they don't cross. Right, so for example, every clique will contain the lowest route and the highest route. Right, and then really there's only two choices of what else I can jam into here. Right, a route like that, or the other clique, right, again, every clique in this framing has to contain those guys. Right, and just a mental check. Right, there are four edges. N is 0, 1, 2, N is 2, so the dimension is 4 minus 2. If it's d-dimensional, I need 3 routes in the maximal clique. So these are the two maximal cliques that index simplices in this triangulation. Let me see if, yes. All right, so this is the picture. Right, for example, you can see this clique, it corresponds to this simplex because it's the convex hull of these 3 vertices. And actually, right, the maximal cliques index the top dimensional simplices, but so the smaller dimensional faces are also cliques, right, just not maximal. So this edge, for example, is that clique. So let me pause here. Any questions? Yeah.
So if you create like a orbital set, you create a partially ordered set where one path is bigger than another, comes before the coherent. Is this the order complex of that order set, or can you have incomparable things which are both less than something?
I've thought about this problem before. I don't remember the answer.
Robinson's complicated.
Yeah.
Are these triangulations coherent, regular?
Yeah. Yeah. So that's shown by Danilov, Karzanov, and Koshevoy.
Right on the heights?
They do give an explicit construction. Yeah. Okay. So I left lots of space in this slide, and when I'm teaching calculus to my students, they know that usually they have to do a lot of work now. Okay, so let's see. This is a graph, and again, sanity check. Images. Here, 0, 1, 2, 3, 4, 5, N is 5, dimension 7. Can you compute a maximum clique? After you've done that, can you compute another maximal clique so that the simplices that they index share a facet, they're adjacent? All right, and here I put in a little comment, can you do this by hand? Or you can code this, it's not too hard to write some program to compute this stuff, but the question is, can you do this by hand? Okay, I'm not actually expecting you to do this right now because that's crazy, right? For just coming up with a clique, you will have to come up with 8 routes which are coherent. And when we did this exercise, it's not so easy to figure out when 2 routes are coherent even when I give it to you. It's harder, even harder, when you just start from nothing and you just try to create some clique so that it's pairwise, every pair of routes is pairwise coherent. But here's one answer. And one of my goals today is to show you a gadget that will let you do this quickly by hand. Eventually, you will be able to come up with this within a minute, just by hand. And I claim that you will be able to, by hand, generate, if you had enough time, you can generate all the maximal cliques of any graph you like by hand. Okay. Right, so a little bit of history. Right, again, in William's talk, he mentioned the Cry polytope, a face of the Birkhoff polytope, studied by Chan, Robbins, and Yuan, known to have normalized volume, the product of the first n minus 2 Catalan numbers. Right, and we're still seeking a combinatorial proof of that. Right, so that was how I got started in this stuff. Not really, I don't have hopes of actually addressing that problem combinatorially, but there were lots of interesting things that we can do, and sort of motivated by that question, just to understand volumes combinatorially, it led me to a lot of this stuff. And so one of the very first examples I ever looked at was a flow polytope whose volume is just one Catalan number. Right? If you're going to attack a problem whose volume is the product of Catalan numbers, maybe you want to start small. So down here, like don't look at the text up at the top, like just down here, these were some of the very first examples I ever computed. Right? I took a graph. I basically did this exercise by hand, but even then it took forever. Right? You change the framing, and then it's like you're starting from scratch because you have no sense of when things are coherent anymore. But one way to try to attack that problem of right, proving that the Cry polytope has product first n minus 2 Catalan numbers is to maybe look at a triangulation structure. Right? If you can triangulate it and you can find one very nice one that somehow explains the product structure, and so far we haven't found such a thing, right? If it has some adjacency structure whose maybe the dual graph of the triangulation kind of has nice combinatorial properties, we can maybe obtain a combinatorial proof. So that's where some of these ideas started, right? So we can study the maximal cliques, right? They index that triangulation. We know when they're adjacent, so we can create a dual graph of the triangulation. Each top dimensional simplex is now a vertex in your dual graph, and you put an edge between two vertices in your dual graph if and only if they share a facet, if the simplices, top dimensional simplices share a facet. Okay, let's see. Yeah, so initially, we just were looking at a dual graph structure, but right, just after computing some of these very elementary examples, we noticed that actually these dual graphs have shapes that are recognized as Hasse diagrams of posets. And so there is a poset structure on that dual graph. Right, so from before, I was saying if two maximal cliques, let's say C and C prime, right, if they index top dimensional simplices that share a facet, then they differ in exactly one route. So I can start with a clique C, delete a route, add another one, right? But this means they're in conflict. Right, P and Q are in conflict necessarily because these are maximal guys. Right, so pictorially, what that means is there exists some vertex so that the relative orders of incoming P, outgoing P are different from the relative orders of incoming Q, outgoing Q. Right, so I'm just going to define an order by saying if I have the situation where P and Q conflict, right, if when P leaves, it's smaller than when Q leaves, then P, that the clique that contains C, the clique that contains P is smaller than the clique that contains Q, and this is a covering relation because I only switched out one route. Right, and the transitive closure of this defines a partial order.
Excuse me. Yeah, this maybe was a question. That may depend on V, the way you define it, right?
Yeah, it may depend on V, but this is a minimal conflict.
Like take the minimum?
This not minimal V, except.
In this situation, yeah, there will be only one.
Yeah.
So they will only coincide in one part of the route and the rest.
Yeah, because these are maximal cliques.
Yeah, I trust you.
Yeah.
How do I know that they are in conflict with some?
If they weren't, right, if P and Q were not in conflict, I could have put this into my maximal clique.
But they could be in conflict with some other.
It doesn't happen because C is maximal. Yeah, it's not obvious. But, so one more time, you can kind of stare at these pictures. I can explain these pictures a little bit more, but maybe it doesn't make any sense right now, but yeah. Right, so as flow polytopes, again, these are high dimensional, so every simplex has dimension 4. Okay. Yep, I just made them bigger. Okay. Right, so in some joint work with Matisse van Bell, Rafael González, and Francisco Mayorga, we first started just studying variations of this, right? Pick a graph, study its flow polytope and its triangulations, and see what kind of triangulation structure you get. So one of the first things we did was a new generalization of the Tamari lattice. So here, right, nu we just fix to be some vector with non-negative integer coefficients. And I'm going to create this graph. My authors like to name graphs with names that I can't say properly. This is the caracol graph because it looks like a snail. We would all be in real trouble if they let me name these graphs and I just name it something in Cantonese. But this is the caracol graph. Right, so the construction, for example, is down here, right, I have a Hamiltonian path. I have one edge going to the sink like that. And up here, this notation just means they're multiplicities. Right? Whatever that vector was, it's telling me, right, how many edges go here. So these are multiple edges with that many copies, VA copies over there. Right, when that new vector is just 1, 1, 1, 1, 1, that recovers the classical case of Catalan things. Right, so I'll say more about that in a second. For example, the pictures that we saw here is the special case when nu is 1, 1, 1, 1, 1. That's just classical Catalan stuff. But now we get new Catalan stuff. If I look at the planar framing, it turns out that the dual graph is the Hasse diagram of what that means is an order ideal in Young's lattice generated by a partition of this shape. Now, I'll give you pictures in a second, but nu defines a partition, and I'm just looking at the order ideal generated by that partition in Young's lattice. Okay, flip these arcs up here, change the framing so it looks like that. We called it the length framing, but anyhow, the dual graph turns out to be the Hasse diagram of the new Tamari lattice. More pictures in a second. And so we were able to biject these maximal cliques, depending on the framing, to various nice families of objects enumerated by the new Catalan number, which can be computed as a determinant of this matrix of binomial coefficients. Right, in special cases, there are nice formulas, but in general, you can only compute this with a determinant. Right, so they're new Catalan many maximal simplices, so the volume of this flow polytope is new Catalan numbers. And we were also able to compute the H star vector. It turns out to be the new Narayana polynomial. So the new Narayana polynomial, the kth coefficient is, for example, the number of dict paths of a certain staircase shape, above a certain staircase shape, with kth valleys, for example. And so a little bit more detail, looking at that planar framing. And so the key to showing that some particular flow polytope has some particular volume of some known combinatorial quantity is to biject to known combinatorial objects. So one of the first things that we found out was that routes in, I stole some old slides and didn't update the notation. So routes in that graph are in a one-to-one correspondence with lattice points above nu. Right, so here's an example. Right, nu here would actually be 2, 1, 0, 3, and I think the convention is 0, but it doesn't really matter. That last coordinate doesn't really matter. And so you can see that the multiplicities of those edges correspond to nu. All right, I can form a lattice path based on nu. Right, so north, east, east, northeast, north, no east, north, 3 east, and so on. Right, so I'm going to be looking at dict paths that lie above that region. Right, and I claim that if you just look at any route, for example, I'm just going to pick a random one, that corresponds to a lattice point that lies weakly above this picture. Right, and the key to doing that is to encode these regions in the following way. With these bounded regions in the graph, right, this tells me that because I drew a route, right, that lies on top of 3 of these and 3 of these, then it corresponds to that lattice path, or that lattice point. All right, so for example, if I just took the highest route, that would be this lattice point. If I took the lowest route, it doesn't lie on top of any e's and any n's. That lowest route would correspond to that lattice path. And so that's the bijection. But we know that maximal cliques are a collection of coherent routes. Right, so what does it mean to just take a coherent route and plot every single one of these routes as a lattice point? So the coherency condition translates to dict paths. And for example, this is a maximal clique, and then using, right, however many north and east regions it covers, the correspondence gives me a dict path like that. Right, and it turns out that switching a clique, right, if I remove some route, put in another coherent route, that corresponds exactly to pushing a peak, a valley to a peak. Right, the other one, the story is similar. Right, there is that same correspondence between routes and lattice points. Right, that is independent of framing. But then the framing tells you which collection of lattice points are coherent. And it turns out that when you change the framing, and I, again, just stole old slides, forgot to update, right, visually just flip all of these up. This is that other framing. All right, but so in that other framing, this one, coherent means they are actually the configuration of a new binary tree. And so this appeared in some work of Cesar, Arnau, who am I missing? Camilo? But yeah, so coherence in this framing gives us new binary trees. Oh, and yeah, I should mention, adjacency, right? Adjacency of 2 maximal cliques corresponds to a tree rotation. Okay. Here's just a lattice. This would be the planar framing. I drew things kind of weird here, and some of it still doesn't make sense at this point, but that's okay. Right, this is the new Caracol graph, where nu is 1, 2, 1. Right, and you can see there is a bijection to the order ideal generated by this partition. So that will be one of the exercises. Can you, after we learn what this means, right, can you go directly from whatever the diagram that is to these partitions? So one of the takeaways is that triangulations unify the study of the Tamari lattice and the post-set of order ideals of the type A root lattice. And that's just another way of describing this lattice over here. Right, and for a very long time, my training was originally in symmetric functions. And in symmetric functions, the only Catalan object structure that I ever cared about was this one. I never found a reason to care about the Tamari lattice at all because I'm not a geometer. But then I discovered this stuff and I realized it's basically the same thing. So now I can think of the Tamari lattice, it's basically the same thing as right? Why did I care about this thing originally? It's the dominant regions in the Xi arrangement, for example. But now I can think about these two things on equal footing. They're just triangulations of the same graph, same polytope, with a different framing. Right, and both of these are lattices. I know this is not a lot of evidence, but even back then we were already thinking, well, maybe all of these dual graphs actually have a lattice structure. Right, and the more computations we did, right, we were never able to break this conjecture. Right, so a little bit more evidence. If you studied the icosahedron and the Tamari lattice, a very natural thing to think about would be the weak order. And the S weak order was introduced by Ceballos and Pons, right, which they defined as a lattice of S decreasing trees. I forget, maybe you guys did increasing trees in your decreasing. At some point, I read something that was S increasing, and I was like, ah.
Yeah, he did.
Okay. But some kind of tree, right? It's a generalization of binary trees, and they conjectured that the S weak order can be realized as the one skeleton of a polyhedral subdivision of a polytope. In joint work with González, Morales, Philippe, and Tamayo, we gave 3 different ways to realize this. Right, the first one is related to this talk. If I look at, again, Spanish words with R that I can't pronounce correctly, the oruga graph. So how do I construct the oruga graph? I first start with just the oruga, caterpillar, and bumps. And then depending on the S vector, and here I'm assuming that each SI is at least 1, right? I add SI minus 1 extra copies of edges that kind of snake in between in the framing, like that. So that's the S oruga graph. You look at its DKK framings. The dual graph has a Hasse diagram of the S weak order. And then there are some other geometric realizations of this. Right, the last one came from tropical geometry. But this is yet more evidence that DKK triangulations have a dual graph whose dual graph has a lattice structure. And so here's a picture of the oruga, the S oruga, where S is 1, 2, 1. That conjecture is now a theorem. It was proven independently by Bell and Ceballos and Berggren and Serhiyenko around the same time, using different techniques. All right, so that DKK triangulation that posted on max cliques is actually a lattice. And I think, moreover, Mathématiques and César proved that this is an HH lattice. So in particular, it's congruence uniform and semi-distributive. So it has lots of nice properties. They call this a framing lattice because it depends on the framing of a graph, and you look at the flow polytope triangulation. But basically, it includes a whole bunch of other lattices that people care about. And I've seen, so Matthias van Bell was my grad student. I've seen him give talks where he has this gorgeous diagram of how all these things are, they fit with each other. But here are some examples studied by lots of people in this room. Okay. Any questions at this point? Yep.
If you change the framing just slightly, you have all the triangulation.
Jonah knows the answer, right? So when you change just one framing on one edge, how does that change the triangulation? I know he's been studying this problem.
Yeah, so you talk about doing like very small changes to the framing, and it seems like this preserves certain things. So there's, for example, there is a conjecture of Rencontres who said that your number of linear intervals is preserved when you do any changes to the framing, and this has been since proven. And it seems like there's more structural stuff that is preserved when you do this. Like you can sort of think about like you have a lot of same things in your lattice, but you're sort of like shifting things around a little bit. But it's still a little bit unclear what's happening structurally.
So I guess not a complete answer yet. Right, so the first part of the talk, maybe I've tried to convince you a little bit that cliques are hard to work with, especially when the dimension goes up and your graph looks complicated. Right, the goal here is to come up with another combinatorial object that encodes these maximal cliques, or well, just cliques in general. They don't have to be maximal. We'll encode it in a more compact manner. Okay, some more definitions. I have a graph, right? These are the vertices. I'm going to define the subset of slack edges to be just the edges that are smallest on the outgoing order. All right, so 3 edges leaving here. The smallest one is a slack. And I'm just going to index slacks by the vertex they leave. So if I just index the lowest ones, we've got n slack edges. Everything else we called a split edge. And I'm just going to choose some kind of ordering. It can really be any ordering that you like, and split edges, I will just call them T sub something. Right, so slacks are the lowest ones, splits are the upper one. This terminology came about because if you think about netflows again, right, if I send one unit of flow into here, and you look at maybe a cut of your graph across these edges, right, you always have to have one unit of flow. And somehow that means we have a slack edge because this, for example, that edge, the flow is completely determined by the other two. And so they're kind of slack variables for us that came out from some other work, but that's where the terminology came from. And here, right, I've added a little appendage to my graph at the beginning. It will be helpful more for really the proofs to add an inflow half edge x. So I'm calling this edge x. It doesn't come from any vertex. It just kind of exists. It goes into the source. And so note that the number of split edges is the dimension. Okay, this denotes the set of permutations of a set B. Then the set of partial permutations is just the disjoint union of all the permutations of subsets of A. And if I have a function from, think of this as an augmented edge set. This will be more important for tomorrow's talk. Right, I start with a graph whose edge set is E, and then now I just add this inflow half edge. I define a function on it whose values are partial permutations. So I really want to think of partial permutations as words on the alphabet A with distinct letters. And so to each edge, I'm assigning some word. Right, its support is just the edges that have non-empty word. So, permutation flow. A little bit more terminology. At a vertex V, let's say I have incoming edges E0, E1 up to EI, so maybe a picture something like this. E0 up to EI. And let's say at the vertex V, I have a bunch of outgoing edges. E0 prime, E1 prime, EJ prime. Remember, these are ordered sets, right? So this has an incoming order, and this has an outgoing order given by the framing. Then the Vth incoming summary, right? So I've defined I've put some words on these edges, right? Pi of E. Then the incoming summary at V is this ordered list of words. Right, so pi E naught, pi E1, concatenated. Same thing with the outgoing permutation, outgoing summary permutation. I just take this in order of the framing and I concatenate the words. So a permutation flow is then one of these functions. I'm assigning words to the edges that satisfy these conditions. Right, so that incoming half edge, can fix my slides on the fly. Okay, that incoming half edge, it will always be assigned the value 0, the letter 0. That initiates the flow. And then at some V, incoming edge set, outgoing edge set like that, the outwards permutation, the outgoing summary, is an unshuffle of the incoming summary together with a possibly empty subword of E1, E0 prime, E1 prime up to EJ prime. Okay, that's a lot, but what's going on is, if I just add a little bit to this picture. All right, so I have an incoming summary here, pi E0 concatenated with pi E1. Then to create the outgoing summary, I'm allowed to shuffle this word with some subword of these letters. Right, and that shuffle can be just an empty subword as well. You might be wondering why that's gray, and that's because some of my co-authors would prefer to call this an unshuffle. He says, in algebra, this is called an unshuffle, even though combinatorics call it a shuffle. So I told him, yes, I'll call it an unshuffle, but this is how I'm gonna do it. So depending on your taste, it's an unshuffle or shuffle, but it's exactly what you do with cards, right? You have a deck of cards and you just put them together, maintaining the relative order. Okay, one more condition. Right, let's say I've chosen some subword of this to shuffle with my incoming permutation. If this letter, one of these letters, is shuffled into the outgoing permutation, then it must be the first letter on its edge. Okay, I'll have lots of examples in a second, or at least a few. Okay, I want to make sure I don't mess up this example, but it's actually okay if I mess it up too. Give me just a second. All right, I'm going to create a permutation flow. And for reference, I've just put the way I've labeled the edges, the slacks and split edges over here for reference. Okay, we must have the initial flow must be 0, permutation flow. And then I decide, right, I have an incoming flow, I decide which letters I want to shuffle with. All right, so I can shuffle with the letters 1 or 2, according to this. Okay, I'm going to pick just a shuffle with 1. All right, so if I shuffle with 1, right, then 1 has to be the first letter of its edge. It has to be the first letter of that edge. Right, and now I have a choice of where I want to put 0. I can put it on this edge or that edge. I'm going to choose this one. Okay, at vertex 1, I'm going to choose to shuffle with 3 and 4. Right, these are the letters. I'm going to choose to shuffle with 3 and 4, and 3 and 4 must be the first letter on their edge. Right, so I'm really allowed to put 0 anywhere I like. I'm going to put it down here.
You could have put it after the 4.
I could have put it after the 4. I could have put it after the 3 as well. At this point, I'm really shuffling like that. So not super exciting yet. And this is a small example. Okay. In the next vertex, 4, 1 is the incoming word. I'm going to shuffle with 5. And so here I'm going to shuffle. And 5 has to start that edge. Right, so now I can either have 4, 1 here, or 4, 1, or even 4, 1. And I'm going to choose this one. Right, keep going. At vertex 3, the incoming edges, I follow the framing, so the incoming permutation is 3, 0. And I'm going to shuffle with nothing. Right, that's one of the possibilities. I can shuffle with a possibly empty subword. I see why I was confused. I confused myself. That's a typo. That E0 should not be there. Slack edges, I don't shuffle. All right, so up to this point, I followed the rules right. I just wrote it down wrong. But at each vertex, you can shuffle with the labels on your slack edges only. And so the E0 should not be there. Anyhow, 3, 0, shuffle with nothing. I'm just going to send the flow down there. And then finally, I'm going to take the incoming summary 4, 3, 0, 5, 1 and shuffle with 7. Right, I have that choice. I'm going to choose to shuffle with it. 7 must start on its edge, and I can choose to shuffle this way. So this is a permutation flow. I did make a mistake. Hold on. It's okay. I made a mistake in the sense that this doesn't fit what comes next, but that's okay. But this is a valid permutation flow. I just looked at the wrong diagram. What I meant to construct, I just added an extra 5 by accident. What I meant to construct was this guy. But here's another example. I'll just let you stare at it for a second. And so one more time, you initiate the flow by sending in a 0. At every outgoing permutation, you have a choice of what you want to shuffle with, maybe all of it, maybe nothing. If you choose to shuffle with something, it has to start its own edge, on its own edge, right? And then you just keep going. Any questions?
Could you say again what the choice of S's and T's were? I mean, your given graph had all those edges, but you called some of them S's and T's.
S, the lower edge is a slack edge.
The very lowest.
The very lowest one in the outgoing order on the framing. It's not necessary to encode a lot of things about the flow polytope because it's a slack variable. Right? Somehow we only need to keep enough information, and enough information means I only need the actual edges, not the slack edges.
I'm sorry. In the labeling of the non-slack edge, the labeling is arbitrary.
Arbitrary.
So
Yep.
all of this follows the arbitrary ordering you pick?
Yeah. Here, so the arbitrary ordering I picked was 1, 2, 3, 4, 5, 6, 7. You can give me any arbitrary permutation of those labels you like. But
Once it's fixed, everything else is
yeah. Yeah, if you wanted to call this T6 and T3, then that first step, I will be shuffling 0 with some subword of 3 and 6. And then your, right, the actual numbers you're working with changes, but the structure actually doesn't change. Later on, the choice of that initial way we label the slack edges, it matters if, for example, you sit in on Nathan's talk on Monday and he mentions 3-1-2 avoiding permutations, and that was something I never thought about. But there is a way to draw a picture of this guy. You can choose a labeling that lets you see the 3-1-2 avoiding really easily. And I did work out the conventions that I needed to make that happen. I didn't have time to LaTeX it. 3, 1, yeah, so here you see, well, it'll come later, right? You see a 3-1-2 on this edge, but there is a way to choose a convention to see it really quickly that it's 3-1-2 avoiding. Okay. These are the solutions to one of the exercises. So I'm just gonna keep going. Right, so what's coming, right? I've been trying to hint at what's coming. These permutation flows are supposed to be encoding cliques. So we have, for maximal cliques, or sorry, wait, we're not there yet. So for cliques are ordered by containment. I also want to be able to define some containment order for permutation flows. And this comes from the concept of a split reduction. Okay, we've really overloaded on some of the definitions. At some point, I think we decided we were going to call everything a split, so then everything would be true. But then it just made everything really complicated. So we just have kind of two things that we call splits. This, before I define split edges, right? You give me a graph G, these T's are the split edges. Now I'm going to define a split in a permutation flow pi. Okay, a split in a permutation flow is just an edge if its first letter is E. Right, so it's related to splits in the other sense. And then an edge is a direct split of E at V if this diagram happens. Okay. Vertex V. Here's some split edge. So necessarily, pi of t has to begin with that letter. Right, but we say t is a direct split of the letter E if I have some edge below t, where E is the largest possible edge where this situation happens. And what do I mean by this situation? E is the last letter on that edge, right? And this is as high as possible. And so I say T is a direct split of E. And here I'm assuming that E came in from here. So one of the subtleties here is that E is not the same as E star. I'm not sure that detail matters at this point. But okay, I have a permutation flow. What are the splits of pi? Mm-hmm.
So E can appear only on one edge. What is
E can appear on many edges, right? For example, if E is 1, E can appear on...
No, I mean, all those edges at least.
E can only appear on one of the edges, yes.
What do you mean by the largest? Like on the one point? The largest for all edges.
So there could be other edges. Star, I don't know. Just other edges, and there could be other letters. And so what is, if this was the situation, then I would say T is a direct split of C. Yeah, so there are no more, it takes a lot of words to try to write this down. I was hoping a picture would make it clear, but maybe not. Right, there are no more edges in between here. So here's a caveat. There could be an edge. You'll see in the diagram in a second. There could be an edge. Let's say it's T5, and I have the label 5 there, and that's the only label. T is not a direct split of 5, because 5 just started here. There is no 5 flowing in. Yeah, so in this scenario, T is a direct split of E. Mm-hmm.
You can also have edges with no labels, right?
Have just...
That don't have a permutation attached to that. Like in your...
yeah, it could be empty.
They don't count and you read below?
You read below, yeah. Yeah. If they're empty edges, like this picture right now, you would just keep going below. All right, so what are the splits of this pi? With this as a reference for what I'm naming the edges. We want the edges whose first letter is the index for that edge. One, yeah. T3, T4, T7, yeah. Right, all the letters that show up in the permutation flow. What about the direct split of the letter 0 at the vertex V1? In this case, right, 4 immediately follows E. A 0, 4 follows 0, so the direct split of 0 at V1 is 4. If it's this scenario, T is 4, E is 0. And then the last one, the letter 3 at V1 is a direct split of what? 0. Yeah, that's what I was clarifying with Vincent.
So in the second sentence, it's the direct split. The direct split.
Yep. Yeah, this doesn't count. 3 is not a direct split of 4 because 4 didn't, there's no history of 4 is another way to think about it.
Is the previous to last sentence? It's not the direct split, it's the direct split afterward.
Ah. Thank you. Okay, we're trying to come up with a containment order on permutation flows. I say that pi is a split reduction of rho if pi can be obtained from rho by doing some operations to its letters. Right, so I'm thinking right now that this is what should be happening. Right, and what I could do is start with a bigger one. I should be able to maybe keep a letter. That's okay. Or I might want to delete a letter. But how I delete a letter depends on whether there are direct splits of it. If I want to delete a letter that does not have direct splits, I can just delete it. Otherwise, if it does have a direct split, right, if T is a direct split of that letter, then I can delete all the E's after V where they split, and then replace all the T's by E's. So delete and replace. And the claim is this operation defines a partial order on permutation flows, and containment is a weird symbol, but because it mirrors cliques, then we're using the containment symbol to denote this partial order. And so I can obtain pi as a split reduction of rho, then I say pi is contained in rho. Because secretly, these permutation flows encode cliques. I will tell you how to recover them. Okay. All right, so I've just copied the definition of a split reduction. And rho here is a maximum permutation flow. We're going to try to show that our pi that we've been working with is contained in rho by a split reduction. Okay. So it's a little bit small down here, but I'm going to try. Right, so I'm trying to somehow keep letters or delete letters according to those rules. Right, I know I need to get pi, I need to delete that letter. Right, so I'm going to go ahead and just delete 0. Do I want? Yeah, okay. I'm going to delete 0. But because at the vertex 0, 2 is a direct split of 0, I now have to follow by replacing all of 2's by 0. And so wherever I see a 2, I will go ahead and replace with a 0. Okay, I keep going. Again, this is my target. This looks good so far. So I move on to the next vertex, and I see I have some labels here, nothing down here. So I want to delete 4. Okay, so let me just copy what I have up to that point. Okay, at this point, I need to delete 4 in hopes of getting anything that looks close to that. So just delete 4. But did 4 have a direct split? It does. 5 is a direct split of 4, so I have to replace 5 by 4. Okay, one step closer. I look at the outgoing edges here. To match this, I need to delete 6, and nothing splits from 6, so I can just go ahead and delete it. And then what's left is pi. Right, so this shows that pi is contained in rho by split reductions. For the cube, not the cube, the square, this is the face lattice indexed by permuflows. By the way, the term permuflow was inspired by the permutrees of Vivian and Vincent. Let me see. Let me just take a look. I'm just going to skip that for now. Right. So the claim is these gadgets that I've just devised, they are in bijection with cliques in a framed triangulation. Right, so that means I need to be able to, if you give me a permutation flow, I need to be able to recover the clique that it encodes. Right, so at least I will tell you how to do that. All right, so again, the pi permutation flow that we've been working with, I want to, so you'll notice that the outgoing permutation at the end, I can draw it here, it doesn't matter. That's the outgoing permutation at vertex n. It has 5 letters. Each one of them encodes a route. Right, so this is not a maximal permutation flow, it just encodes a clique of rank 4. Right, some of the reconstruction is easy. For example, if I follow the letter 0 all the way back, that's a route. That's one of the routes I keep. So the route 0, I just do this. Right, what else is easy? 1 is easy, right, because 1 also starts at the beginning, so I follow the letter 1 backwards. That gives me another route that's in the clique, that's encoding it. Okay, those are the easy ones. Now it gets a little bit trickier. Right, for example, 3. If I follow 3 back, well, 3 ends there. Right, how do I complete that to a route? So let me just draw that suffix. That's where direct splits come in. I look at what it's a direct split of, and I follow that direct split backwards. Right, before, we were saying that 3 is a direct split of 0. I then have to follow it backwards. That defines a route. Keep going, right? I can do that to 4. Follow the letters 4 backwards. 4 is a direct split of 0, so it also continues that way. Okay, 7 is the fun one. It's because 7 is so short. And so you follow the direct, it's a direct split of 4, so I follow 4 back. Now 4 ends, but we know how 4 goes, because 4 is a direct split of 0, so basically you just keep tracing back those direct splits. And I claim that permutation flows encode coherent routes. All right, so there's a bunch of stuff to be checked. One of the things is we should be able to construct an inverse map, or check that the containment order is satisfied. We will do this tomorrow, and the easier way to do this is actually kind of a big leap. How did, right? We didn't just come up, we didn't just come up with this object and said, hey, it encodes routes. It went the other way. We started here and figured out the permutation flow structure. So in the middle, there are lots of intermediate steps that kind of make that transformation easier. So that will be some of the content of tomorrow's talk. And actually, yeah, let me stop there today, and I'll kind of recap and pick up from there tomorrow and introduce A-flows as well, general A-flows.
Thank you. Are there questions, Martha? Use the mic.
I had one quite earlier when you talked about new dig paths. If you take the 3D picture or higher dimensions, what happens to the graph? Is this
the graph
or the polytope? Like, what's the analog if you generalize them, or is this clear or no?
So I'm not sure what you mean by. Let's see.
So if your path is three-dimensional, then you don't just have two directions, but you have three. What is the...
You mean lattice, like a three-dimensional lattice path? I have no idea.
Okay.
That's interesting.
No questions?
So at a certain point we said that 3 was a direct flow of 0 at 1, something like that.
Mm-hmm.
Okay. But isn't there the edge labeled with 4 in the middle of
Yeah, so there's some technical definitions for just for working with this stuff. That technicality actually doesn't matter so much. That direct split idea just lets me know how to recreate these routes from the end. Right, so let's see, let's go here, right? What I really need is a concept to let me be able to start from some permutation and recover all the routes given that thing. So I just need to know if I follow some letter back, if it ends here because this is the edge T3, right? How do I continue backwards to get a route? The idea is to follow the letter. So for example, let's make this really crazy. I don't know. I'm just making stuff up that doesn't make sense, right? But if this edge only contains 4, but let's say all these letters were incoming somehow, right? You have all those letters coming in. I need to know how to continue, and maybe there are more. Right? Let's say that was a scenario, right? I need to know how to continue this route 3. The way I continue is to pick the letter that's closest to it in the outgoing permutation. Right, so the outgoing permutation is the concatenation of, now I have multiple letters, I know, this is terrible, but I'm concatenating that lower word with the middle word, with the upper word. Right, so I'm looking at kind of the closest letter to 3. Does that make sense?
You really don't want to have 4.
I know I really don't want to have 4, I know. When I wrote that, I was like, 16. Now it really doesn't make sense. All right, so this is the outgoing permutation. All right, to be able to continue 3, I just need to know how to do it in a way that produces coherent routes. The splits are key. And so notice, right, this 4, it was born here. It originated there. There are no 4s incoming. Right, so 4 is not important here. It doesn't tell me how to continue any route backwards. But somehow I need to continue backwards from the thing that's closest to it. And that's the next closest one. Does that make sense?
Yeah.
Just a quick one. So I'm not sure on the partial order. So why is the bottom element less than the second one I put?
Yeah. You noticed that I had a preferred order. I'm not sure I can make this very rigorous, but there is a way to think about, I think Cesar and Matthias called this rotation, clockwise or counterclockwise. You can obtain one route to the next one by some kind of a rotation. Maybe this one would be, I'm actually not sure. Yeah, so the short answer is there is some kind of an ordering. I can't explicitly explain it right now.
Maybe we can work this out during the exercise session. Any last question? If not, let's thank Martha again.